Hi everybody, welcome to the 1.6 notes. Today we're going to be talking about how to determine a limit using algebra and algebraic manipulation. So in the last couple of days we've been learning properties of algebra and we figured out how to find a limit if you have a table or a graph. However, the most exact way to find a limit is for you to use the equation. And so there's a process to doing this, and because of the nature of limits, sometimes it's really easy to find a limit using an equation, and sometimes it's really complicated. So I will walk you through that. So if you were asked to find a limit and you were given an equation, the very first thing you do is you are going to evaluate the limit. So you will start by evaluating the limit. What I mean by that is plug in whatever x is approaching to the equation. So for example, if you have like the limit as x approaches 3 of some function, you would plug in 3 in for x. There are about 3 things that will happen if this occurs. And so our first option is the option that you want to get, because if you get this option, you're done. And that's you get a finite number. So that means like you plug in 3 and you get out 6 or 1,000 or negative 2/3. You get a number that is finite. The other thing you do is if you have a rational function, you could get some number that's not 0 over 0. So for example, you get like 4 over 0. This means, and we'll talk more about this, that you have an infinite limit. And then the last option, which tends to be most complicated, is you get 0 over 0. And we talked about this last week, if you remember. But this is called indeterminate form. And that's the most complicated, and that's the one that has to use the most algebraic manipulation. So let's go on to option 1. If this happens, you were done, and that finite number that you received is your answer. This tends to happen with functions whose domain is negative infinity to infinity. So if you had like a function y equals x plus 3, if we look at these 2 examples down here, we have x squared plus 3x minus 3, which is a quadratic. We have cosine x, which is more complicated, but still has a domain of negative infinity and infinity. And so, I didn't realize I wrote that already. Sorry. So just think about functions that have no level of discontinuity. Another thing that this means is that the function's value and the limit value are the same. That's why this works so nicely. So for example, let's say that we wanted to find the limit as x approaches negative 5 of x squared plus 3x minus 3. All I have to do here is plug in negative 5 squared for x. And I will get 25 minus 15 minus 3, and that equals 7. And that's what the limit is. So in this example, the limit as x approaches negative 5 of x squared plus 3x minus 3 is 7. Also, say that this function right here we called f of x. F of x, f of 3, or sorry, back up. F of negative 5 also equals 7. So if you get a finite number, that means that your limit and your function value are the same at that point. And if you were to look at the graph of this, it'd probably look something like this. And negative 5 would be like maybe right here. This is just a sketch, and that would be 7. So that's an example. That function, there's like no gaps or holes or anything, and so everything works out great. I feel like cosine we tend to think is a complicated function, but it's really not too bad. If I were to plug in cosine of 3 pi over 2 here, where I'd be at on the unit circle, if you can picture the unit circle right here, I would be at this point right here. Cosine goes with x. X is 0 there. So cosine of 3 pi over 2 is 0. So that's what the limit is. And that's also what the function value is. And sorry, yeah, that works good. Okay. And then the way that this graph would look if you were to sketch it, just so we can kind of like reinforce this idea. Sorry, I should have gave myself a little bit more space here. And try to write a little smaller. Oops. Okay, sorry, that took me so long. Okay, so pi over 2 pi, 3 pi over 2. Every time you label like a cosine function, just do it this way because it will work better in the long run. And then cosine of 0 is at 1, cosine of pi over 2 is 0, 3 pi over 2 is 0, and then cosine of pi is -1. So your function's going to look something like this. And at 3 pi over 2, that's the function's value. And as you approach from the left and the right of 3 pi over 2, you're going to approach 0. And that's what the function is telling you graphically and algebraically. Now is our next combination, which is you got not 0 over 0. So again, you got something like 7 over 0 or -12 over 0. This means you have an infinite limit. So your limit is either going to be approaching infinity, negative infinity, or it doesn't exist. So it could be negative or positive infinity. I'm going to add that there. If this happens, the best thing that you can do is you need to find the limit using a graph or a table, but you can do it algebraically. And so I'm going to show you how to do it algebraically here. I'll first show you the graph and then I'll show you how to do it algebraically. So the way that I would do this function is you could, if you know how to graph this, I know that because if you plug in like -4 here, that's going to equal 0. So I'm going to have an asymptote at -4, so I automatically know that. But if you were to graph this using a calculator, what you should get is a function that looks something like this. And so just based off of that, I know that this answer is going to be does not exist. But maybe you're on the section of the calculus exam, or you're in college, or you're on one of my tests, and you're asked this question and you don't have a calculator. Also, real quick, just to show you, if I were to plug in -4 here, I would get 2 times -4. And then I would get -4 plus 4. So I have -8 over 0. So that's why I know it's an infinite limit. And the reason it does not exist is because as it approaches from the left of -4, it goes up. And the reason and from the right, it goes down. But let's say that I didn't know what the graph looked like. Again, I didn't have access. What I would do is take a number, and you don't actually have to work it all out, but take a number really small, like on the left of -4. So a number that would be on the left of -4, that's a little smaller, is -4.001. Let's do that one. Okay, and I'm going to plug in -4.001 here and add 4. So this is just kind of an idea. This would give me -8.002, and then on the denominator, I'd get 0.0001, and it's negative. So basically, we have a 8. Yes, it's 0.002, but we have like -8 divided by -0.001. And if you ever divide a whole number by a fraction or a decimal, you're going to get a larger number. So for example, if you would have done 8 divided by 1/2, you would have gotten 16. If you would have done 8 divided by 4, you would have gotten 32. So, 1/4, you would have gotten 32, because there's lots of 1/2s and 8s, and there is lots of 1/4s and 8s. And so there's lots of 0.001 and 8. And so that number is going to get really, really large. And so I'm estimating that from the left side, it's going to approach infinity. And I don't have to create a whole table, and I was able to do that in my head. You also need to know what's happening on the left side. So a number that's just a little bit bigger is like -3.999 plus -3.999 plus 4. Well, on the numerator, it's going to be like, this is hard for my brain right now. It's probably like -7 point something. It doesn't matter. It really doesn't matter. So this is what I'm trying to show you, is I can't think about that right now, but it doesn't really matter. It's -7 something. And this is going to be -3.999 is a little bit smaller than 4, so it's going to be 0.001. So now I'm taking -7 and I'm dividing it by a decimal, a really small fraction. And but because it's negative on the numerator and positive on the denominator, this is going to approach negative infinity. And so that's how I know that it does not exist, is because if I look from the left and I look from the right values of -4, they're different. One's going towards positive infinity and one's going towards negative infinity. And so that is a way to do this if you don't have the graph or access to a calculator that could show you the table. This one is an example. Again, if I plug in 0 there, I'd get 1 over 0 squared, and you can't divide by 0, and so it automatically does not exist. But can we be more specific? And so if you were to look at the graph, there would be an asymptote right down the middle at x equals 0. There's a vertical one because you're dividing by 0, and that's what breaks the function. And the graph is going to spike up like this. And as you can tell by looking at that graph, you would get infinity. And I just know that because I know this because I've done this a long time. but you could just put that in a graphing calculator. But again, if we want to use the last idea and we want to try to figure out, okay, like what's an estimate of the limit from the left side, right? I could plug in a number just slightly smaller than 0. So I'm going to put in like negative 0.001 squared. So I have this whole number 1, and then when I square that, it's going to become positive, but it's going to remain a fraction. It's going to remain a number smaller than 1. And so this is going to get really, really big eventually. And then the limit as x approaches 0 from the right. I'm just trying to, this isn't like the best math ever. I'm just kind of trying to think about like, what do I imagine would happen? Same thing. This is going to get really, really big. And so that's a way that I can tell that the answer is infinity. And so a lot of times when you get these problems, you will have access to a calculator that could show you the table or a graph. But if not, this is how you would do it by hand. Our last option tends to be the most complicated option because there's still ways to go on. But this is, I got 0 over 0, and this is called indeterminate form. One thing to note is as you guys try out these problems, if I were to plug in 5 here, I'd get 5 squared minus 25, and then I get 5 minus 5. And then 5 squared would be 25, 25 minus 5 would be 0. And I'd get 0 over 0. AP Calc does not like this notation because technically you cannot equal indeterminate form. It's not a real number. And so if you ever do this and you figure out that it equals 0, 0, do not write equals. Just do like an arrow off to the side indicating that you can tell it's indeterminate form. But they don't like you writing equals and they won't give you credit for that. But if you do get indeterminate form, that doesn't mean that your limit doesn't exist. It just means that you're going to have to use some algebraic manipulation or look at the graph/table to figure out the limit. And so indeterminate form, often what happens is the function value doesn't exist. So I'm going to write lots of times. This is an example where the limit exists, but the function value does not. And as I sketch these graphs for you, you'll see. So if you want to go and maybe take out your graphing calculator, sometimes graphing calculators aren't great at showing you holes, but if you want to go to Desmos, if I were to graph this function right here, if I were to put it into Desmos, it would look like this. It would be just a linear function, but there'd be a hole at 5, 10. And so if you look at that graph, you can tell that the point doesn't exist there. F of 5 does not exist because there's a hole. But as you approach from the left, you're approaching 10. As you approach from the right, you're also approaching 10. So the limit does exist even though the function value doesn't exist. And so this is an example of how you'd figure it out graphically. And the next couple pages, I'll show you how to deal with these algebraically. Same thing happens here. If you plug in 4 to this function, 4 minus 4 is 0. And then the square root of 4 is 2, and 2 minus 2 is 0. So again, I get indeterminate form. And so you might think, oh, I can't do anything. But if you were to put this graph in Desmos, it would show you a hole at 4, 4. And so the point does not exist, but the limit does. And as we approach 4, the y value, or the function, goes to 4. This one's like a really complicated one. It looks scary, but basically this graph kind of looks like this. It has like just like a bunch of almost like parabolas. They're not parabolas though. And as you get closer to 0 from both sides, if you're using Desmos, you would see a hole, but the function would still approach something, and in this case it approaches 0.25. And so indeterminate form tends to be kind of fun if you like algebra, but it's a little tricky, and what meets the eye isn't necessarily what happens. So now we're going to go on to some practice problems with indeterminate form, because this is the form that we're going to need to practice the most. There's a lot of strategies here. So, using algebraic manipulation to find limits in indeterminate form. So here's our first example. It's the one that we just looked at. So we already know it goes to 0, 0 because it's this first example, example 1 on that last page. So what we're going to work with is this kind of idea of removing a discontinuity. If you think about the function, the reason it's breaking is because if you plug in 0 to this function, you're going to divide by 0. It doesn't matter that the numerator is 0. It matters that the denominator goes to 0. And so you're kind of thinking like, well, what can I do? So what we're going to do here is I'm going to write this function out, and I'm going to figure out, can I remove a factor? Can I cancel out a factor and so that denominator is no longer there, because that denominator is what's breaking our function. So I'm going to start by, this is a quadratic. Anytime you see a quadratic, maybe for you, I naturally think, what if I factored that? So if you look at that numerator could be broken up into factors. It is an example of a perfect square quadratic. So that first term is a perfect square. A is 1. That's the coefficient in front of x squared, and 1 is a perfect square. And then 25 is also a perfect square. It's also a difference of perfect squares. So you can only factor differences of perfect squares. You can't factor sums. But x squared minus 5, what that would factor out to be would be x minus 5 times x plus 5, because the square root of x squared is x and the square root of 25 is 5. Oops, I did a mistake that you always have to make sure you do, okay? So make sure that as you go on, you continue writing x limit as x minus 5. I just did that mistake and I'm glad I did it, but I will take off points for that because it's not precise enough. And so if you look here, these two functions are equivalent to each other, but their limits are also equivalent to each other. And what I can do is, if you see that factor x minus 5 is on the numerator and the denominator, anything divided by itself is 1, so I can just cancel these out. And I'm going to get the limit as x approaches 5 of x plus 5 now. Now, if I plug in 5, my function's not going to break. It's actually going to give me out an answer. And so if I plug in 5, as soon as I plug in this value right here to the function, I no longer have to keep the limit signs in anymore. So I'm plugging in 5 for 5, and I'm going to get 10, and I can drop those limit signs now because I've actually evaluated the limit. And that was what we got from up there when we looked at the graph. So the answer to this one is 10. These two functions, I just want you to know, these two functions are not the same function. Obviously, they're not the same because the first function has a hole at 5 and the second function doesn't have a hole at 5, but they do have the same limit. So they're not the same function, they're not equivalent to each other, but they do have the same limit. And so that is how you do these problems. We're going to, in class, look at more complicated factoring problems, but just to start off with, we're going to make them on the simpler side. So we're going to go on to our next page. This is another factoring problem. The reason I know to factor is because it's a quadratic. That is like really what indicates to me that it's a quadratic. Or if it was a polynomial, I would think to factor. So for this one right here, if I were to plug in -2 here, I'm going to work this out real quick. I would get 4 plus 8 minus 12. 4 plus 8 is 12, so 12 minus 12 is 0, and I would get 4 minus 4, and that's 0. So I do get indeterminate form. You don't, if you just know, you don't have to do that, but sometimes these problems you're like, oh, it looks like it could be in an indeterminate form, and then you actually do all this work and it's not actually an indeterminate form. You could have just like plugged it in to start off with. So what I'm going to do first is, it looks like both of these functions, the numerator function and the denominator function, can be broken down because their factors aren't separated right now. So I'm going to start over here with x squared minus 4x minus 12. And the way that you do this is you think about the way that you factor a trinomial, a quadratic trinomial, is you think what multiplies to -12 and adds to -4. So that would be -6 and 2, because -6 times 2 is -12. -6 plus 2 is -4. And because the a value, so when I mean the a value, I'm talking about this right here. Because it's 1, it's really easy to factor. I just do x minus 6 and x plus 2. But if it was anything else, it'd be more complicated, and that's what we'll do more in class. The denominator, the denominator is easy to factor because it has a greatest common factor. X is in x squared and 2x, so I'm just going to factor that out. And I'll be left with this. So I'll be left with the limit as x approaches -2 of x minus 6 times x plus 6. Sorry, the factor of x minus 6 times the quantity x plus 2 divided by x times the quantity x plus 2. Notice, if you do this right, a lot of times it's like you can tell because we have this shared factor that can cancel out, and that was the problem. Negative 2 is what was breaking. That factor was like what was breaking our problem because negative 2 plus 2 is 0. And now I have the limit as x approaches negative 2 of x minus 6 over x. And now when I plug in negative 2, everything works out. I get negative 8 on the top, negative 2 on the denominator, and that equals 4. And so as soon as I cancel out that factor that is causing our domain to have a hole, everything works. Okay, we have 2 more sets of problems, and they're a little different. So if you look at this one, same problem is happening. We're still having indeterminate form because the square root of 4 is 2, 2 minus 2 is 0, and then 4 minus 4 is 0. So we still have indeterminate form, but we don't have a quadratic or a polynomial anymore. And so what sticks out to me is the square root right here. And so this square root, because that is there, so this is kind of like our square root strategy. Square root strategy is we're going to do something called multiplying it by the conjugate. The conjugate is, in this case, I have z minus 2. It is basically the opposite of the either numerator or denominator that has the square root in it. Basically, it's the same. Like this part is the same, but the conjugate means you're doing the opposite of the sign. So in the first one, the numerator is minus sign. This time I'll use addition. And so I'm going to multiply by the conjugate. When I do this, there's a couple strategies. My goal, just like the last one, is to cancel out a factor pair. And so my goal is to cancel out something on the denominator because the denominator is normally the problem. That's like, again, what I'm saying, that's what's breaking it. And also, sorry, I did this wrong. Part of multiplying by the conjugate is multiplying by the same thing on the top and the bottom. That's like, because if not, you're changing the function. So what I just wrote was wrong. So sorry, please erase that. But you're multiplying, the reason you can do this is because the square root of z plus 2 divided by the square root of z plus 2 is 1. And so multiplying anything by 1 doesn't change this function at all. It's just we're manipulating it. So that's the key thing. But because we're trying to cancel out a factor in the denominator, we need to keep it as factors so that we can actually do that. And so I'm not going to distribute anything on the denominator. I'm just going to leave it as z minus 4 times the square root of z plus 2. So I'm not actually going to work out that multiplication right now, just for the sake of, it would be a waste of time for us to do that, basically. But I am going to factor the numerator, or distribute the numerator. So first I'm just going to write it like this. We're just going to do this in steps, just for a second. And now what I'm going to do, I'm going to try to keep sometimes I mess around with my 2's, but I'm going to try to keep them consistent because of the z's in this problem. It makes it a little bit more complicated. How do I go back? Okay. This is a 2. Okay, so what I'm going to do now is I am going to distribute the numerator. And so I'm just like basically foiling. I'm doing the square root of z times the square root of z, the square root of z times 2, negative 2 times the square root of z, and then negative 2 times 2. So I'm multiplying everything by everything. The square root of z times the square root of z is just z, because like the square root of 4 times the square root of 4 would just be 4. The square root of z times 2 is plus 2 square root of z. Negative 2 times the square root of z is negative 2, the square root of z, or minus 2. And then negative 2 times positive 4 is minus 4. And then again, I'm trying to cancel out a factor on the denominator, so I'm not going to lose our factor pairs. Now I'm going to simplify what I can on the numerator. If you notice right here, those are the same thing. So if I were to subtract them, they would just go to 0. So they basically just cancel out. And then I'd have z minus 4 on the numerator, z minus 4 on the denominator, times z, the square root of z plus 2. And look, these factors gone because they're the same thing. Now I have the limit as z approaches 4 over 1 divided by the square root of z plus 2. Our z minus 4 factor was what was breaking this equation. And so this is great. That's gone now. So now I just have to plug in 4 for z, and I'll get 1 divided by the square root of 4 plus 2. Square root of 4 is 2. And this will give you 1/4. And that is how you do 1 with square roots multiplied by the conjugate. We're going to do one more of these kinds, and then we have 2 trig ones. So for this one, same process. We have a square root. There, it's now the square root of x plus 4, so there are 2 terms under the square root, but it doesn't change our process at all. And if I plug in 5 there, I'm going to get the square root of 9 minus 3 over 5 minus 5. The square root of 9 is 3. 3 minus 3 is 0. 5 minus 5 is 0. So this is an example of indeterminate form again. And so I'm going to, because it's a square root, that's how I know to do this, I'm going to try to see if multiplying by the conjugate would help. So the conjugate of this is x plus 4 plus 3, and I'm doing that on the numerator and I'm doing that on the denominator because that's basically just multiplying by 1. I'm going to get the limit as x approaches 5 of, I'm just going to write this out in steps. There's definitely a pattern to this if you get the hang of it. So I'm not going to change the denominator at all, but I will change the numerator. Or I'm not going to distribute. The square root of x plus 4 times the square root of x plus 4 is just going to be x plus 4. Then I will have, so that's what I just did there. Then I'm going to do the square root of x plus 4 times 3, which is plus 3 square root of x plus 4. Now I'm going to do negative 3 times the square root of x plus 4, so minus 3 square root of x plus 4. And then negative 3 times 3 minus 9. And now I'm just going to do some algebra, so just follow along. The big idea with these problems is you're basically just doing algebra. Like, not all of this is really calculus skills, it's more of algebraic skills. And that is the answer. 1/6. The hardest part about these problems is just the algebra. So just keep practicing that and you will get the hang of it eventually. Okay, last 2 problems have to do with trig. These are hard, but mostly hard just because we're not as comfortable doing trig as we are doing other things. And so, right now, again, if I were to plug in pi over 2 here, I would get sine of pi over 2 is 1. So sine squared of pi over 2 is also 1. And then cosine pi over 2 is 0. So I'd get 0 over 0. So again, we have indeterminate form. But this is not, I guess sine squared x is a quadratic, but that won't really help us here. Or it's not a quadratic, but like there's a square root sign, so you might think, oh, maybe I could factor. And sometimes you might have to factor, but not in this problem. And then there's no square root symbols, and so you can't use any of the other things. And so what we have to do is we have to use our trig identities. I'm going to show you a website that I found, and just Google these. Like if you ever forget trig identities, just like search trig identities. And these are some popular ones right here. So there's the quotient identity, the reciprocal identity, the Pythagorean identities. Those are like the 3 most popular identities that I would say you have to know. Other popular ones are the sum and difference identities. Those are definitely seen on calculus, and the double angle ones. So I can't show you right now, but the sum and difference and then the double angle identities like are fair game. And so the problem here is cosine, because cosine of pi over 2 equals 0. And that is what I'm trying to cancel out. So I need to somehow change this so I can get cosine to cancel out. And so I'm going back to my trig identities. And cosine of x, the only identity that it has is 1 over secant theta, but that doesn't really do anything for us. But I do have sine squared of x. And so I'm trying to think, okay, is there any identity I have that or incorporates that could somehow cancel out cosine of x? So if I look here, the Pythagorean identities has sine squared theta plus cosine squared theta equals 1. So that is definitely an option. And then the other one I was looking at is the half angle identities or the double angle identities. There's a sine squared there. But those are both like 2 theta, like it's cosine 2 theta, and cosine of 2 theta is different than cosine of theta. So that's not going to help us cancel that out. So the one we're actually going to use is the Pythagorean identity, which is sine squared theta plus cosine squared theta equals 1. And this is one of the Pythagorean identities. Obviously, this doesn't match that perfectly, but if I were to subtract sine squared theta on both sides, in this case x, on both sides, I would get cosine squared, I'm going to change it to x because that's what we're using, equals 1 minus sine squared x. Therefore, and that matches our numerator now. So what I'm going to do is I'm going to replace 1 minus sine squared x with cosine squared x because that is what it is equivalent to based on that identity. And now maybe you can see where we're going because maybe now we actually have a possibility of canceling out that cosine on the denominator. So cosine squared x, that's just equivalent to cosine of x squared. That's just like a fancy way that trigonometrists write that, but this is equal to that. And so that basically means that cosine squared x is cosine x times cosine x. It's like 4 squared. 4 squared is 4 times 4. Cosine of x squared is cosine of x times cosine of x. There, we have some matching factors, so we can cancel one set of those cosines out. I'm left with the limit as x approaches pi over 2 of cosine x. If I plug in cosine of pi over 2, I get 0, and that is my answer. Yes, I took that one. So that is the first example of trig, and those ones will probably be the hardest ones to grasp just because you're not as familiar with some of those identities as factoring and other algebraic things. But last one, we got this. We have the limit as x approaches 0 of tangent of x over sine of x. So if I were to plug this in again, I would get 0 over 0. We just know that at this point. But normally sine is the problem. And so I'm trying to think about like how can I get sine to cancel out? And so if I go back to these trigs, normally if you have sine or cosine aren't the ones that you manipulate because they're like more on the simple side. So if you see one like cosine or tangent or cotangent, that's the one I like to manipulate. And if you look at the quotient identities right here, tangent of theta is equivalent to tangent of theta is equivalent to sine theta over cosine theta. And that seems like that could help us out because it has a sign. So like there's a chance that would help us cancel out. So what I'm going to do here is I'm going to do the limit as x approaches 0. And I'm going to replace tangent of x with sine of x over cosine of x divided by sine of x. So this looks a little ugly right now. I now have like a fraction divided by a whole number. So I'm going to change my sine of x to sine of x over 1. Just so now I have like a fraction divided by a fraction. And the fraction rules are just keep, change, flip. So if you divide two fractions, so I'm going to keep my first fraction, which is this section right here. Keep that exactly how it is. I'm going to change my division right here. That's there. Change that into multiplication. And then I'll flip my other fraction. So I'm going to make this 1 over sine of x. And like we said, sine was the problem. Just like that, we can cancel it out. I have now limit as x approaches 0 of 1 over cosine of x. 1 over cosine of 0. Cosine of 0 is 1, so we have 1 over 1, which equals 1. And that is our answer. So that is a lot of problems. You guys, I'm sure, did great. take your time, look over these. We will continue to practice in class. But that is just kind of the basics of algebra manipulation with indeterminate limits.